A few weeks ago, a friend of mine asked me to explain to them why it is a heavier object will hit the ground sooner than a lighter object if the two objects are dropped from the top of the Eiffel Tower. And so I decided to try and give it a go. In a previous video, I've had a look at trying to solve linear ordinary differential equations, but the air resistance on a larger body falling through the air isn't caused by laminar flow of air around the body, it's caused by turbulent flow. So we have a different equation for air resistance depending on whether it's a very small body and we have laminar flow, or a very large body and then we have chaotic turbulent flow of air around the body. That expression we're using to model the air resistance I've written here. Then you can look that up. It's a pretty standard way of modeling air resistance, where rho is the density of the fluid, in this case air, which is about 1.2, 1.3, let's say 1.2 kilograms per cubic meter. V is the speed the body is moving through the air, the fluid. CD is some constant which depends on the shape of the body. The larger the number, the more turbulence it will cause in the air. And A is the cross-sectional area cutting through the air. So I started in the same way as I started in the previous video, where I looked at laminar flow. And the resultant force on my body as it falls is going to be equal to its weight minus this air resistance term, which I've substituted in here. Now, acceleration is defined as the rate of change of velocity, and I've got a velocity here, so I wrote the differential equation here. Now, I have a lot of constants here, and I wanted to make things a bit simpler, so I thought I'd combine some of those constants together. But before I could do that, I noticed that A, the cross-sectional area moving through the air, is going to depend on the mass of the body. So let's imagine I've got two bodies that have the same density, but they have different masses. Well, then it's reasonable to say that if they're the same shape, the same density, the larger mass one is going to push more air out of the way as it falls. It's going to have a larger cross-sectional area. So I first of all made the assumption that my bodies were spherical. Don't worry about that assumption, because this constant CD can be used to correct for the shape later on. So I've got spherical bodies that are going to fall through the air, and they're going to have the same density. Now, the density of the body, I've used rho p here, because in the original formulation of the problem, they were people falling off the Eiffel Tower, hopefully with parachutes on. But rho p here was the density of the person, which is equal to the mass of the person divided by the volume of the person. This is a big V for volume, not a little v for speed. So just be careful about that. So the volume is 4/3 pi r cubed for a sphere, and I substituted that in here. And then I rearranged to get r as the subject, which you can see here. I then assumed that the area, the cross-sectional area of the air that's being cut by this object as it falls through, is going to be a circle, because the object is spherical. And the area of a circle is pi r squared. So I substituted this value of r into this equation to get this. And then finally, I substituted this area into this equation to get this expression here. Now remember, I wanted to simplify those constants. So I gathered my constants together. I've got a pi, a rho, that's the air density, the CD here, and then I've got 3m divided by 4 pi, the density of the person, all raised to the power of 2/3. And this part here multiplied by pi, rho, and CD, that's all one big constant, which I can call k. So I substituted that k back into that equation, and I get this differential equation here. It looks a bit neater now because we've got fewer constants. And of course, I've got a mass down here and a mass to the 2/3 there, which I can tidy up and just say it's divided by the cube root of mass, which is what this means. Now, solving this differential equation was beyond me. I wasn't sure how to solve it. I looked it up. It was fiendishly difficult. And so I just threw it at WolframAlpha, which gave me this solution here. And there were a few constants thrown in, but all those constants did is shifted the graph of velocity versus time around. I wanted the velocity to be initially 0, so I chose those constants. Basically, I set those constants to 0 so that this is the expression that falls out, and it makes sense. Then what I did is integrated this function. And again, I can't remember how to integrate a hyperbolic tan function. It's been a long time. So I threw it at WolframAlpha. And here we have it, the expression for the displacement as a function of time. How far the body falls as a function of time. And you can see I've got mass included in here. That means that I can use a graphing calculator such as Desmos to look at what happens when I adjust these constants. And that's exactly what I did. So here you can see the graphing calculator Desmos, and I've put two different displacements in here. This displacement here is for mass 1, and that's the mass of mass 1. This displacement here is for mass 2, and this is mass 2. The constant here is the same for both masses, and is calculated with CD, which is that shape factor, which I'm going to use the same for both masses. If they are people, then they're both basically the same shape, or if it's any other sort of object, you can adjust this slider. I decided my gravitational field strength 10 was close enough. And density of the R, I couldn't put rho into Desmos, so I just said R was the density of the air, which was 1.2. The density of the person, I've used a D instead of a rho subscript P. D for density of the person. I reckon a person's mostly made out of water, so I just made that the density of water as a rough idea, 1,000 kilograms per cubic meter. So I've plugged the numbers in that seem sensible. And I've got results like this. The Eiffel Tower is about 300 meters tall. So this says that a 100-gram individual will take about 14 seconds to hit the ground. But a 40-gram individual will take a little bit longer. Just click here and it'll tell me what that is. About 14, nearly 15 seconds. 14 seconds, 15 seconds. So it takes about a second longer for the person with less mass to hit the ground. And I can adjust these sliders to see what happens. As the mass of the person 1 increases, the time it takes for them to travel that 300 meters goes from being less time when we're traveling with a greater mass to more time when we're traveling with less mass. And that seems to make sense. Intuitively, we'd expect a heavier object to hit the ground sooner. So that seems to make sense to us. But we can also adjust some of these other sliders. Now, we would expect, if there's no air resistance, we would expect those two bodies to fall and take exactly the same amount of time. And the way to adjust air resistance in this simulation is to change the density of the air. So if I reduce the density of the air down towards 0, these two graphs should converge towards the same graph, and it should just be a basic quadratic. And as I do that, you can see that's what happens. The two lines get closer and closer and closer. The closer the density of the air gets to 0. The problem is, as soon as I set the density of the air to 0, well, we break this equation. But it gets closer and closer to a quadratic as r gets closer and closer to 0. So there's probably some clever calculus way of saying as r approaches 0, this approaches a quadratic. But I'm not a mathematician. I'm really not. So let's set that back to the density of air. And if we were falling with a more dense atmosphere, then we'd get something like that. Now I'll put a link to the Desmos graphing calculator with these formulas loaded in below, so you can play with these sliders yourself if you want to. But hopefully that answers the question and gives you an explanation of why it is a heavier object does indeed hit the ground before a lighter object.